who is a postdoc at UC Irvine. And Andrew will be talking to us about investigating the effects of land surface composition and land-ocean ratio on the climate of terrestrial worlds orbiting low-mass stars. So take it away, Andrew.
Thank you, Ashley. I hope everyone can hear me okay, and that's coming through. I've got Tara giving me a thumbs up. Yes, okay. Right, well, thank you, Ashley, for the introduction. Thank you, everyone, for putting together such a great program so far, and for inviting me to talk in this next session. The 25 minutes were very generous, but I'm a little worried that I'm going to run out of time, so I'm not going to hang around too much, and I'm going to jump straight in with a quick outline of what I want to discuss during this talk. I'm going to start with a very quick introduction about M-dwarfs, which we haven't explicitly talked about, I guess. I'm a big fan of M-dwarfs, so I'm going to talk about those, introduce them, why I think they're great, and then I'm going to get into some results from our group, particularly led by me, from the last year or so, talking about Albedo feedbacks, the land-ocean ratio on small rocky planets, and then a very recent paper that's in the last stages of review, and I'm going to present some results from that about the land surface composition and heat transport on small land-dominated planets as well. So let's jump in with a quick introduction about what M-dwarf stars are. I'm sure we're probably all quite familiar with that as astronomers, but in case anyone's forgotten, M-dwarf stars, aka red dwarfs, are smaller and cooler than stars like the Sun, for example. The properties are that they have masses around 7 to 50% the mass of the Sun, and they're quite a bit cooler. But the important thing is that they're common. They're common in the galactic neighborhood, comprising 70% of known stars. And this is one of the more popular M-dwarfs, TRAPPIST-1, which I'm going to present some results from later as well. So there's a wide range of subclasses within the M-dwarfs there as well. This is an ultra-cool dwarf, TRAPPIST-1. So a very broad introduction to M-dwarf stars, but I wanted to emphasize that because they're also pretty great planet hosts. So there does seem to be a relationship emerging in the literature or from the data that suggests an inverse relationship between star size and planet occurrence rate. So the planet occurrence rate is just the average number of planets we might expect per star. And I've tried to summarize that here with the figure from one of Gijs Mulder's papers, in which he's kind of collected an overview of planet occurrence rates over the last decade or so. And the trend, while there is some disagreement, the trend does seem to be that smaller stars tend to have more planets, and those planets also tend to be smaller, which is kind of exciting. So this tells me, combining the fact that there are lots of M-dwarfs out there, and the fact that they host many planets, and those planets could be smaller, this is exciting for me as someone who does exoplanet climate stuff and astrobiology, because these might be the planets that we want to look for in terms of habitable environments and potentially life. So normally when we start talking about habitability, this is often the first place that we will start, the first diagnostic, if you will, the habitable zone. And again, I'm sure this is a concept we're probably all really quite familiar with by now, but in case you've forgotten, it's defined as the distance from a star where liquid water exists on the surface of a planet. And you can see from my cartoon to the right of the figure there that it's a region. It's a region that's bounded by boundaries, I guess, and those boundaries themselves are set by output from radiative convective climate models. The input to those models is the assumption that the planet that we're looking at is very similar to the Earth, the same atmosphere, same composition, same size normally, which can be a little bit limiting. And in fact, there is a movement now to maybe start thinking about more and different atmospheric compositions, because maybe just looking at exactly Earth-like compositions is a little bit limiting. And I always recall my PhD advisor always told me that the habitable zone is interesting because it's an astronomically observable feature of a star, but doesn't actually tell us anything about the planets that might be orbiting within that range. So he liked to say, you take the Earth and you put it around X star, and the region where it could be habitable will be the habitable zone, basically. And kind of to reflect that limitation, there are a trend towards many different types now of habitable zone emerging. And this is an example here, this figure from one of Ramses Ramirez's papers, in which he's extended the classical habitable zone, if you will, using hydrogen and methane to add another couple of gases to the very complicated picture as it stands. So I guess the point being, a lot of us on this call maybe, or a lot of us in this conference, now maybe see habitability as more of a holistic, I guess, concept. I've got one definition of what habitability is here from a paper that I worked on, but that's usually the first complicating factor. Habitable for whom? What are we talking about when we even discuss habitability? And this figure here is an attempt to summarize that. It's, I believe, colloquially known as the planets are hard figure, because it really does demonstrate how difficult planets are to do. And it's from Vicky Meadows and Rory Barnes' chapter in the Exoplanet Handbook. And it illustrates the fact that not only do we need to know a lot about the planet, we also need to know a lot about the astrophysical environment that planet is existing in, and also the other bodies in the planetary system itself. And you might look at this figure and say, well, we don't actually know a lot of these things for the Earth, and you'd be right. So it really does emphasize how difficult planetary habitability or even climate research is to do, and it requires these big teams full of incredibly smart folks to chip away at the story in different areas. And that's all I can do, I'm afraid. So I'm sure we'll see this figure again, but for my contribution to the narrative, I'm going to add a little bit to this corner of the Planetar hard figure, talk a little bit about albedo, surface composition, and surface temperature, really. But bear in mind, that this is only a small picture, a small part of a much larger picture. And I'm sure other talks during the session will probably add a little bit to different parts of this figure as well. So bear that in mind as we go on. Right, now I'm going to jump in and talk about some actual science. I'm going to start with spectral energy distributions and the ice albedo feedback. And I'm going to begin with a general statement in that cool stars emit a greater proportion of their flux in the near infrared. I don't think that's too controversial, but you can see it illustrated here with this figure from Elmore Shields, my advisor's paper from a few years ago. At the top, you can see 4 host star spectra. And the one to focus on is the red one, I guess AD Leo, or a quiet version of AD Leo anyway. And you can see the kind of the wavelength of its peak flux, the point at which the output, or in this case the normalized power density, is greatest, is around about 1 micron. Whereas for the hotter stars, that peak kind of wavelength flux is closer to half a micron. So you can see that there's a proportionally greater amount of flux in longer wavelengths. I don't think that's too surprising. It's basic physics, right? This is a cooler body, and therefore the radiation that it emits is in longer wavelengths. But what gets really interesting is when you combine that difference in spectral energy distribution from the star with wavelength-dependent features on the planetary surface, as illustrated by the bottom figure. So you're seeing a number of different kind of surface features, if you will: snow, land, which is here defined as kaolinite surface, the ocean, blue marine ice, and that's their albedo, i.e. their fractional reflectance as a function of wavelength here. So if we were to look at half a micron, for example, on the snow spectrum, you would see an albedo of nearly 1. Nearly 100% of the energy incident on that snow surface at that wavelength is being reflected away. However, if you look closer to, say, 1.5 microns, for example, the albedo of snow and ice is actually very much lower, less than 0.2, and actually lower than the land surface here as well, which is something to remember for later on in this talk. So the snow and ice albedo actually gets lower than the land surface in longer wavelengths. So we could say in general that ice and snow are more absorptive at longer wavelengths, where coincidentally Dwarf output is quite high. So putting that all together, and focusing on the ice albedo feedback, we can kind of see how the interplay between the spectral energy distribution and the kind of reflective properties of the surface can come into play in destabilizing or stabilizing the climate. So Elmore's paper from a few years ago looked at aquaplanets and the ice albedo feedback there. So a quick introduction to the ice albedo feedback, if you're not familiar with that, is it's a positive feedback that happens on the Earth, well, when it happens on the Earth anyway, and there seems to well, for example, let's say we have some perturbation that cools the planet down. We have ice forming at the poles. That ice has a higher albedo than the land surface. It reflects some energy away and therefore cools the planet down a little further, which results in more ice forming and more cooling, and so on and so forth. And there is a tipping point in latitude, somewhere around 30 degrees from the equator, where so much energy is being reflected away that basically you get an ice albedo runaway feedback, where ice advances all the way from the pole to the equator. There's some evidence that maybe this happened on Earth in the past. So what Elmore and team did for a few years ago was looked at how this operated on aquaplanets around small stars. And they found that the strength of the feedback is lessened. The ability to resist the perturbation, I guess, is lessened around dwarfs. And the reason for that is because of the interaction between the wavelength the SED from the star and the wavelength dependence of ice, which happens to be kind of more absorptive at longer wavelengths where much of that flux is. So Omo found that M-dwarf planets require a much greater reduction in installation to basically enter this ice albedo feedback. But I don't want to focus on that. I want to focus on what we actually did in a paper that came out last year now in AppJ, in where we took that same kind of philosophy, but instead of focusing on aquaplanets, i.e. the planet at the bottom right there, we wanted to incorporate a variable land fraction to see how the land ocean ratio would have affected this feedback process. So we built a simple one-dimensional energy balance model that's one-dimensional in latitude. It has a sea ice component, which is kind of important for ice albedo stuff. If you've done any climate work, you're probably familiar with these kind of models. We used the same albedos for land, ocean, and ice that you saw in the previous figure from Omo's other paper, and the same stellar spectra as well. This is basically a summary of the entire paper. I know there's quite a lot to present here, but I'll try and guide us through it quite quickly. If we look at the figure on the left to start with, the global mean surface temperature is a function of land fraction. There's a couple of things to note there. Firstly, kind of ignore all the symbols. Those symbols denote particular land ocean configurations that we were interested in highlighting. But the key is kind of the solid lines. Those represent linear fits to thousands of simulations. So those are the ones to focus on. And note that they are also color-coded by spectral type. So the general trend in these figures is that as you increase land fraction, you decrease the global mean surface temperature. I don't think that's too surprising. And the reason for that is illustrated in the figure on the right, which shows the bond albedo, so the kind of wavelength averaged albedo for the planet as a function of land fraction. And it shows as you increase your land fraction, you also increase the albedo, which is not a surprise as land is more reflective than ocean is. So you do get this response that we would expect, but you do get an interesting spectral effect as well. So if you look at the difference between the M-dwarf case, for example, that solid black line, and the F-dwarf case, which is the solid blue line, you'll see a marked reduction in surface temperature for a given flux and given land fraction. And that is because of the difference in albedo that's illustrated in the figure on the right. So a couple of things to note on the figure on the right, there is two inflection points in the G and F star cases. You can see round about 0.89 and 0.82. And what this is basically the ice albedo feedback kicking in. So as we get more and more land on those planets, the albedo goes up to such a degree that so much energy is being reflected away that the planet enters a runaway ice albedo effect, basically, and ice advances all the way from the poles to the equator. And you can see that quick and rapid increase in albedo that represents that. And that occurs at around about 82% or so fractional land coverage for an F-dwarf planet. The same happens for a G-dwarf, like the Sun, but you can have a little bit more land before that process kicks in. It's about 0.89 or 89% land coverage before the albedo of the land kind of swamps the signal and results in this rapid increase in albedo. Interestingly, this doesn't happen for the K-dwarf. You can increase the land fraction, the albedo does go up, the temperature does go down, it gets very cold, but you don't get ice advancing all the way from the equator to the pole. Now, the real takeaway point that I want to emphasize here is what's happening with the M-dwarf, the black line at the bottom. You can see there's a shaded triangle there above about 0.7 in land fraction. And what's happening there is actually the ice albedo effect at this point reverses, and it becomes a stabilizing feedback, which was kind of surprising. We were interested to find that. And what's basically happening, imagine we're advancing beyond 0.7 land fraction. As we do so, the average albedo, or the bond albedo, or the planetary albedo increases beyond the ice albedo that we would expect ice to have on a planet at that distance around that type of star. So that dashed line is actually the ice albedo that you're seeing there, that horizontal line. And as the land fraction goes above 0.7, the land albedo kind of swamps that, and it's more reflective. The land has a higher albedo than the ice does. So what you're seeing is, you can imagine there's a cooling event and some ice forms at the pole, but that ice is actually darker than the surrounding land, which then results in the planet warming up slightly, melting that ice and revealing the more reflective land surface, which then cools the planet slightly, resulting in ice forming and so on and so forth. And you get this nice little stabilizing feedback, which we were fairly surprised to find. We thought that was kind of cool. So a quick summary of that paper. There are quite a lot of caveats that I can discuss. It's a relatively simple model, and we could probably have done the water vapor feedback a little bit better, but we're pretty confident that there's something interesting going on there in terms of the energy balance, and you can use a simple model even to find those kind of things. But the next paper I want to discuss is one that's currently in the final stages of review, I hope. Just a few more changes to the text on my part to make, and then we should be good to go. So pretty much fresh off the presses, even though it hasn't quite reached the presses yet. Okay, I want to talk about land surface composition in this part of the talk. So how does what the land is made up of affect the climate of, in this case, land planets, which I'm defining as a planet that's covered entirely by land, pretty obvious there, which we can contrast with the aqua planets at the bottom. So in order to investigate this question, we carried out a number of simulations for the TRAPPIST-1 planetary system, focusing on TRAPPIST-1D, E, and F. And we used the CESM2, the Community Earth System Model 2 3D GCM, combined with ExSoCal, which is a climate model that's kind of specifically modified by Eric Wolf to allow it to kind of work for exoplanet simulations. This is primarily an Earth model, but we need a little bit of modification to allow it to do tidal locking, for example. We then used broadband albedos for 4 terrestrial land surface compositions that we selected based on their frequency or their distribution on the Earth, and also if they were interesting in terms of their wavelength dependence, basically. And we stuck with iridisol, calcite, dune sand, and granite as surfaces. We also had a couple of aquaplanet controls, and we used 2 host star spectra for comparison. But the thing to note here is that these are planets that are entirely covered by land, and entirely covered by one single material, and are entirely flat. So a lot of assumptions going into this. A lot of it is to do with how the model is set up and what we can change at the moment. But we wanted to do it this way for 1, computational efficiency, and 2, allow us to get basically the strongest spectral response that we could get. So bearing in mind these are homogeneous and flat, kind of like Kansas, I guess, or Norfolk in England, where I'm from, and made up of a single material, which isn't probably realistic, but something to bear in mind. Okay, so there's a lot here, and I apologize for all the text as well, but I only really want to focus on the central figure, which shows the global mean surface temperature as a function of bond albedo. I shouldn't actually say global mean bond albedo, that's a bit of a contradiction, but we're looking at basically albedo as a function of temperature there. And I've color-coded the symbols by the land surface type. So the black symbols are granite, the green symbols are calcite, the blue is this iridisol, kind of dry, evolved soil that we find in many places across the world, and the orange is dune sand. So again, a very dry, evolved sand, primarily made of silica and such. But we noticed very quickly that the calcite and the granite provided our 2 kind of end-member cases for our albedo responses, really. The calcite was very much the brightest, if you will, and the granite was the darkest, had the lowest albedo. So we did more simulations with those to bound our distribution, because it is quite computationally intense, this model, and we kind of inferred that the others would kind of fall in the middle, which they did. So the thing to note here is, unsurprisingly, the calcite, because it has a higher bond albedo, the surface temperatures were lower. Nothing really too surprising there. Because the granite had a lower albedo, the surface temperatures are higher there. We also wanted to investigate, as I said, the spectral effect. So we simulated TRAPPIST-1E, both with the TRAPPIST-1 spectrum and the solar spectrum, imagining TRAPPIST-1 was around the sun, for example. And you can see that we've illustrated that using the kind of gray line with the solar symbol next to it. So that simulation there is taking TRAPPIST-1E and basically putting it around the sun with a granite or calcite surface. And you can see there is a bit of a spectral effect. It increases the albedo somewhat, and that decreases the temperature a little bit. But what I really want to emphasize is our focus was on the heat transport. We expected to find a difference in an average surface temperature because we're changing the albedo, but what we wanted to see if there was a non-linear process taking place that affected actually how heat was being moved around the planet. And again, quite a lot to take in here, but let's focus on the figure on the left to start with, which illustrates the day-night temperature contrast as a function of global mean surface temperature. So recall these are tidally locked planets, right? So there's one side that's constantly facing TRAPPIST-1, and the other side that's constantly facing out into the cosmos. And the side that's has all that incident radiation is going to be very warm, and there's going to be some heat transport around the planet. And that's what we're trying to capture here with our day-night temperature contrasts. So again, we've color-coded the symbols by the land surface composition. So if we just focus on the green and the black ones, for example, you can see the calcite has a lower global mean surface temperature, again, as we would expect, but also a lower day-night temperature contrast. So a more homogeneous across the planet kind of temperature distribution compared to the granite surface, for example, which we, again, expected to be warmer, but it also has a greater temperature contrast. So this could be pointing towards efficiencies or inefficiencies in heat transport across the day-night kind of boundary, if you think about it, sort of zonal transport. It's the two smaller figures on the right. We've separated the planet now into the day side and the night side. We're looking at equator to pole temperature contrasts. So this was basically looking more at the kind of meridional transport, I guess. And again, we see that same pattern where the calcite is cooler, both in the day and the night, as we would expect. But the temperature contrasts are again lower, which suggests maybe more efficient heating or heat transport for those planets. The same thing holds for the night side, even if it is a little bit messier. And another thing to note here is that, again, we wanted to look at the spectral effect. So we simulated TRAPPIST-1e using a solar spectrum, which is designated as the kind of upside down triangles that you can see. And there is definitely a strong spectral effect there when we simulate that planet using a solar spectrum. The day-night temperature contrast goes up quite a bit, as does the equator to pole temperature contrast. So just purely changing the incident spectra really does have quite an effect on how heat is being moved around this planet without changing the temperature a huge amount. And that is kind of summarized by this figure here. And I apologize for the wall of text, and I'm aware I'm running a little bit out of time. So I won't be able to get into as much detail as I can. But we're talking here about synchronously rotating planets, i.e. those that are tightly locked to their stars. And you can separate those planets into a number of different rotational regimes. So I don't mean rotation of the planet themselves, but the atmospheres are rotating. And these can be classified as slow rotators, rapid rotators, or Rhines rotators, which is kind of a transitionary kind of regime between slow and rapid. And this is done based on these kind of the ratio between these kind of hard to understand non-dimensional kind of scale lengths. It's basically the size of the features in the atmosphere relative to the scale over which those features can be influenced by the rotation of the planet. But the important thing to note here, or to take away from this figure, is that we found that if you change the composition of your land surface, you can change the rotational regime of your planetary atmosphere, which is quite a big deal. For observations, for example, you would see different structures. Rapid rotators are much more associated with weak convection underneath the substellar point. You might see banded cloud formation. Compare that to slow rotators that would see this more thermally direct circulation, which was what we were seeing, right? This more homogeneous temperature distribution across the planet. So by just changing the surface composition, we could actually change really how the atmosphere was moving heat around, which we thought was quite an interesting result. And it was the calcite that did it, right? If the planet is cool enough, it tends to drop it out of either one of the other rotational regimes into the slow rotator regime. And you can see, again, we've grouped the symbols by color, again, for the different compositions, and then by symbol type for the different planets. So we assume TRAPPIST-1d is in a rapid rotating regime, except if you make it a calcite planet, which pushes it into this rather unique slow rotator regime. And the same could be said for TRAPPIST-1e. TRAPPIST-1f seems to be a slow rotator no matter what we do. But it does suggest that we need to know what's going on the land surface, because that will have a big influence on how the atmosphere is structured, which will then knock on to observations and spectroscopy and so forth. So I'm going to have a quick takeaway from the first paper, which was about how the ice albedo effect comes into play. A few summaries from the more recent paper. Do look out for it in AppJ, hopefully be out in a few months. And I'm going to leave it here with my thank you slides. And thank you all for being here and for your attention. Thank you.
Great talk. All right, so anyone has questions, please post them in the chat. I'm not seeing any yet, so I'll go ahead and start with my own question. So you mentioned clouds a little bit, but yeah, how do you think clouds can affect this, and like, will it dampen the effects of the surface, and how much have you thought of that?
Always, I'm always thinking about clouds, right? Clouds are so difficult to incorporate in this. Certainly in the one-dimensional model, there was an assumption that when we reduced our land surface spectra, that there was cirrus clouds involved. When we put it through the spectral mapping tool, for example, there was an assumption that there was some clouds, but it was purely albedo effects. CESM can do clouds fairly well, but because our planets were completely desiccated, very dry, entirely land planets, there was a negligible amount of water vapor. And that was a big limitation of this paper. We think that, you know, if you introduce a little bit of water even, that this could have certainly effects on the cryosphere and ice formation as well. But you know, clouds are fundamental, right? And I'm hoping that someone smarter than I will be able to incorporate them a little bit better in these models moving forward.
Awesome. Still no questions, so I'll ask a second one.
It was just very clear, obviously.
Yeah. So do you have ideas for potential future missions that could potentially, like any observational signatures that could be accessible in the future?
Observations for me are a little tricky, as people don't let me near telescopes. I've been in and around telescopes, but not, you know, interacting with them in any meaningful way as a climate modeler. So I mean, I'm excited for any observations. The more we can have, the better. But I think in terms of improvements in the modeling work, clouds, as you pointed, are probably going to be a big thing. But specifically for us, we want to have CESM handle variable land-ocean fractions a little bit better than it can. That was a big limitation for us. And again, thinking about how you put continents on the surface, where you put them, how you distribute them, what they're made out of. That's, I think, going to be our next step anyway.
Gotcha. Awesome. All right. Well, let's thank Andrew again.
Thank you.
Keep an eye on the chat in case any questions pop up later. So let's move into the next.